Continuing our lesson, we have in this question the rectangle ABCD, which has the vertices shown. Now what we want to do is determine the point of intersection of the diagonals, then determine the equation of the line that each diagonal is on, and show that the point of intersection is on both of those lines. So here's how we're going to do it. We're given the points A, B, C, and D. So we graph them, A, B, C, and D. In this question, note that one unit for graphing purposes is 2 grid squares on both the x and the y axis. Now the diagonal is the line that goes from A to C, as well as the line that goes from B to D. And what we're going to do here is look for a point of intersection. Looking for that point of intersection, it would appear that it's at an x value of 1.5 and a y value of 0.5, right there. So I would say that the point of intersection is approximately 1.5, 0.5. I say approximately because you can never be 100% sure with graphs, but we can be, relatively sure. Now we're going to try and confirm that algebraically. So what does that mean? Well, first we're going to determine what's the equation of the line from B to D. In other words, what's the equation of this line? Well, we have 2 points. We have the point B and the point D, so we can come up with the equation of that line. The line from B, which is 1, 4, to D, which is 2, negative 3, would have a slope given by y2 minus y1 over x2 minus x1. So the slope would equal negative 7. So we would know that the equation of the line was y equals negative 7x plus b. We could then sub in either point 1, 4 or 2, negative 3. I chose 1, 4. And we would then see that letting y be 4 and x be 1 would indicate that b had to be 11. So the equation of the line from B to D would be y equals negative 7x plus 11. We then want to find out if the point of intersection that we claimed is actually on that line. So is the point 1, 5, 0.5 on this line? Well, plugging in 0.5 for y and 1.5 for x, we see that we get the equation 0.5 equals negative 10.5 plus 11. This is actually true. So because of that, the point of intersection that we claimed is on the first line at least. Well, let's see if it's on the second line. Well, the second line we want to come up with is the equation of the line containing A and D. Going back to our graph, remember that A is here, and C, sorry, I said D, but I meant C. A is here and C is here. Well, we want to get the equation of that line, and then find out if the point 1.5 comma 0.5 is on it as well. Well, how do we do that? First of all, we get the slope. M equals y2 minus y1 over x2 minus x1. We get 5 over 5, which is 1. So the equation of the line is y equals 1x plus b, or simply y equals x plus b. We want to sub in either of these 2 points and solve for b. So subbing in the point 4, 3, we get 3 minus 4 is b, or in other words, negative 1 equals b. So the equation of the line containing A and C is y equals x minus 1. We then ask, is 1.5 comma 0.5 on that line? Well, letting y be 0.5 and x be 1.5, we ask ourselves, does 0.5 equal 1.5 minus 1? Yes, it does. That's true. So therefore, this point is also on the second line. Oh, I put the bracket in the wrong place there. It should say 1.5 comma 0.5, and I should close the bracket there. And that's also on the second line. So that means that the point of intersection that we found graphically is confirmed algebraically to be on both lines. And that's what the question asked us to do.